So our first talk is by our first lecture in a mini series is by Hanson Smith, who will be speaking about algebraic number theory.
All right, thanks so much, Alvaro. Yeah, so thank you all for coming. I'm really excited to be talking about a little algebraic number theory, and I'm let's see, what should I say? I think first off, I've never quite done a like boot camp 4-day crash course in algebraic number theory, so it might be a bit all over the place, and we'll definitely talk about some things without proving them and so forth. Otherwise, it's hard to build all of algebraic number theory in 4 50-minute lectures. What else? If you have any questions, please don't hesitate to ask. This is not supposed to be this kind of thing where you're supposed to come in already knowing what I'm going to say, or I hope not. Otherwise, I'm going to say some very stupid things. Probably, in any case, I'm going to say some very stupid things. But so please don't hesitate to ask questions. Yeah, I think that about gets it started. Also, apologies, I've never really quite done a lecture like this on the iPad while in person, so please forgive me for any weirdness or whatever that comes across. Usually I'm used to like bouncing around and stuff. Okay, cool. So let's get started. Number theory, very, very broadly, is the study of the integers and equations involving the integers. So that's awesome. And I want to try a little bit to motivate, or at least give some utility to how we get from the integers and equations involving the integers to the main objects of study in algebraic number theory, which are called number fields and number rings. And they kind of seem a little bit weird from the perspective of just thinking about 1, 2, 3, 4, -7, that set of numbers. Okay, so yeah, first off the bat, the integers we denote by this blackboard bold Z, and it comes from the German word Zahlen, which means it's the word for counting, so makes sense. We're going to study the set of numbers used to count. Okay, and let's see, what can we do? We can add, subtract, and multiply. We can't always divide, and sometimes you want to divide. Of course, want to divide by something other than 0. And when we want to do that, we introduce the rational numbers. We denote them by this blackboard bold Q. It's a over b, where a and b are integers, and b is not 0. So that's the rationals. And oftentimes it'll be useful to do some work in the rationals and then try to scoot back into the integers to finish our result off. It's nice to be able to divide. And Q comes from quotient. So we're taking quotients of integers. Yeah, so there's some somewhat goofy links thrown throughout these notes. And also these notes are very rough, and only the first day can be even vaguely trusted. And so I'll keep adding to these as we go on. I had ambitions to write them all before the course, but of course, sometimes we fall short of our ambitions. So I'll try to spend some time on notation, because I think one of the biggest barriers to anything is just getting used to all the weird notation we use. Okay, so I'm interested in studying the integers, and by extension, studying the rationals. So, and I'm also interested in studying equations involving these sets of numbers. Some of the simplest equations we can think about studying are polynomial equations. You just have one variable, and you have coefficients coming from the integers, say. So the ring of polynomials, I can add, subtract, and multiply polynomials as well, so they form a ring. With integer coefficients is denoted z adjoin x, and if I want rational coefficients, I denote it q adjoin x. Okay, and so going a little bit backwards from how this field originally developed, we're going to start with some definitions, and then we'll try to see why these definitions are useful for us in our study of the integers and things involving the integers. So the first definition is a number field, and that'll be a finite extension of Q. And we often denote a number field by the letter K, and K comes from the German word Körper, the umlauts, it's a tough one for me, which means body. And that's one of the rare German words that actually has like a nice Latin root, corpus, corpse. So it's a body of stuff. It's all knit together. And you'll notice in algebraic number theory, a lot of the people who built this field were Germans. So there's still a lot of German influence in the nomenclature, at least. Okay, so a finite extension of Q, that's nice. But to be a little more concrete, I could take, if I have a number field of degree n, that means I have degree n as a Q vector space. So I have some vector space over the rationals with degree n. What I can do is I can find a monic irreducible polynomial. Monic means leading coefficient 1. And I'll be really interested in monic polynomials. And I can find it in the integers, and I'll let alpha be some root of that polynomial in the complex numbers, say. And so I can take Q join X, and I can mod out by this polynomial, declare that polynomial to be equal to 0, and see what I get. And I'll get something that looks like this. So I get a nice, basically I get a nice basis for this Q vector space, this degree n Q vector space, in terms of 1, alpha, alpha squared, alpha cubed, all the way up to alpha to the n minus 1. So I get a nice power basis for this number field as a Q vector space. And one thing just a kind of personal aside, one of my research areas, and we'll learn more about this, is when we can have a nice power basis for the analog of the integers that we're about to define as a Z vector space. And of course, depending on what you've heard about before, we can't really do a vector space over Z, so we call it a Z module, a module over the integers. Okay, cool. So that's number fields, and that's our analog of the rational numbers. So we have a nice analog of the rational numbers, and we really care about integers, right? So we have this analog of the rationals. We ask for what's the new analog of the integers inside of this analog of the rationals. And we'll see when I crash. I have a serious caffeine addiction, and I haven't had near enough caffeine this morning. So at some point I might crash. Okay, so you can ask, what's the analog of the integers? And there's a lot of reasonable ways to answer this, and historically there were a lot of potential answers, but I'm just going to cut to the chase and tell you what the quote unquote right answer in this case is. So how do we think about the rationals? Well, I can think of the rationals as the set of solutions to all linear polynomials in Z adjoined X. And ax plus b is a nice linear polynomial, and that corresponds to the rational number given by the root of that polynomial, minus ax over b. Or whoop, I think that should be minus b over a, right? See, well, I'm nice. It's cool. I'm writing, so I can say that should be minus b over a. Okay, cool. So I can make corrections on the fly. That is kind of nice. Right. So that's how I can think of the rationals, as these roots to linear polynomials. And then the integers. What are the integers? Well, they're they're rational numbers without denominators, so they're roots to monic linear polynomials, leading coefficient 1 polynomials in Z adjoint X. Okay, so let's just generalize this definition. I have my number field K, and then I'm just going to take the set of roots in K, of elements of K, that satisfy monic polynomials in Z adjoint X. And that'll be my definition. And I know, at least for me, when I first saw this, this was not a very enlightening definition. I don't even know this is a ring yet. There's some work to do to show if I take two of these elements and multiply them, they'll actually satisfy another monic polynomial in z adjoint x and so forth. I'm going to spare you that and just say, believe me, it's a ring. But yeah, it's worth actually playing with these things and getting a feel for what's going on. And I'll say I like to denote them with this curly O sub k. And that notation goes all the way back to Dedekind, who is one of the people who built algebraic number theory. And it comes from the German word Ordnung, which means order. And today, I should point out that this is a little confusing because today we call orders any finite index subring of the ring of integers. And we'll explore some examples where we have a nice subring that's not the full ring of integers. So that's just a little bit of kind of historical note and how we normally use the term order. But we denote the full ring of integers with this this O right here. And one thing, another piece of notation you also see is just a z sub k. Okay. So just a kind of first question to get us warmed up and make sure we even understand this definition is, why are the integers a subset of any ring of integers? Well, I mean, I know it's scary. We're just starting first lecture answering. So I'll oh, okay. Oh, yeah. I'll pick on you. I know I can pick on you. Awesome. Yeah. The integers are in the rationals, and the rationals live in this number field, right? Just let b1 through bn minus 1 be 0, and here I have all my rationals. And then the integers, of course, satisfy polynomials that look like x minus a. So that's a nice monic polynomial with integer coefficients. So they live in OK. Okay. Okay. So let's see. How do I do this? I think I go like this, and I go like this. So I want to do really work on some examples here, and as is unfortunately a common thread with my teaching, I always run out of time. But these examples are really kind of pretty key, so we're going to spend some time on these examples. So we want to figure out what the rings of integers of these two number fields are. So that's the goal. So Q adjoined I. Let's see, Q adjoined I. What does this look like? Well, it's a Q vector space. This just looks like R plus SI with R and S, nice rational numbers. Okay. And I is one of the roots of x squared plus 1. And an important thing is, kind of an important side note to note here is I and minus I are both roots of the irreducible polynomial. That's some ugly handwriting. X squared plus 1. So as we go on, it'll be important thinking not just about one root of this polynomial, but thinking about all the different roots and kind of playing with all these different roots of a polynomial and using that to get more information about what's going on. Okay, so this is our nice number field, and we want to figure out what the elements are in here that are analogs of the integers. So the question becomes, what elements in Q adjoined I satisfy monic polynomials with coefficients in Z? So that's our question. That's what we need to solve. Okay, so I'm just going to take a generic element of my number field, r plus si, where r and s are just rational numbers. And I'm going to build a polynomial that it's a root of, and I'm going to just brute force try to figure out when those coefficients are going to be integers. So take r plus si, and I got x minus r plus si. And I want to build a polynomial with this is a root. And if s is non-zero, I need to do some work here because this is a complex number. It's not a nice integer or rational. So the kind of secret is I'm going to take its conjugate. I'm going to look at what happens when instead of I take negative I in there. And we'll try to explore why this works and give some more justification for this, but I'm going to take its conjugate. So I got x minus r. Instead of plus si, I take the other root of this polynomial minus I, so I got minus si. Okay, cool. And I'm just going to multiply out and see what I get. So I'll get x squared. I got minus 2rx. And then I'll have plus r squared minus a negative plus s squared. All right. So this is now a polynomial that's in the rational numbers. Got rid of that I. So this is good. We're getting somewhere. And I want to figure out when this polynomial, and it's monic too. That's great. So I'm really cooking with grease. But I need to figure out when these coefficients are actually going to be honest to goodness integers and not just rational numbers. Okay, so first off the bat, we need these coefficients not to have any denominators. So I need 2r to be an integer. So we need 2r and z. Okay, that's great. And maybe we get lucky and just r is in z. And so I guess I'll say note, if r is in z, then of course 2r is in z, r squared is in z. And so immediately, in order to have this be a polynomial with integer coefficients, I'm going to need that s squared is in z. So I'm going to need that s is actually in z. So if r is in z, we have to have s in z. And if we have r and s both in z, then this polynomial is a perfectly nice monic polynomial with integer coefficients. So that shows us that if I take the set of elements a plus bi with a and b and z, that this is a subset of the ring of integers of q adjoint I. And one way we denote this right here is just z adjoined I. You know, we could think of the polynomial ring over z with the variable I, and of course I squared is minus 1, so we're back to z. So we denote that z adjoined I. All right, cool. And I'm gonna, spoiler alert, this is actually the whole ring of integers, but we want to kind of show that. We want to get our hands a little bit dirty here. So what else can I have happen? This 2r needs to be in z. Maybe r is not in z. Maybe r is an odd number over 2. So I'll change color here. Maybe r equals odd number over 2. So I don't know. I'll write this like r naught over 2. Okay, so that's fine. Let's see if I can do this computation here. I always manage to mess this up. So this coefficient works out if r is an odd number over 2. And then we have this r squared plus s squared, and we need that to be in the integers. So I need, and I can expand out r squared plus s squared. We need this to be in z, and this is going to equal r naught squared over 4 plus s squared. Okay. And so we want this to equal some integer m, say in Z. And I'll write, I guess I should probably expand out, let me put another page in here. Cool. So I should probably say, let's let S equal S naught over, it's got a denominator, let's call the denominator D. And so now I have something like, with all this, I got R naught squared over 4 plus S naught squared over D squared. And I have that this equals M. Okay, so I'll clear out these denominators here, and I'll end up with R naught squared times D squared plus 4 S naught squared equals 4 D squared M. Okay. So I know R naught is odd. So if I take this whole thing mod 4, I figure out that 4 needs to divide D squared. So 2 divides D. Okay. Now, if I take this thing mod D squared, well, I figure out that D squared divides 4 S naught squared. Okay, might as well assume I wrote S naught over D in lowest terms. So that D squared doesn't divide my S naught squared. So we get D squared divides 4. So so yeah, we need that D equals 2, or I guess, yeah, D equals 2. And then, let's see. So the whole thing, we end up with R naught squared plus S naught squared over 4. And I need that to be in the integers, right? So I need 4 to divide S naught squared plus R naught squared. And I know those are both odd numbers. R naught squared plus S naught squared. Okay. So what are the squares mod 4? Well, 1 squared is 1, 2 squared is 4, 3 squared is 1, 4 squared is 4. So the squares mod 4 are 0 and 1. These are odd numbers. I'm in trouble. So I need 4 to divide 1 plus 1. Doesn't work out. Anyway, that was a long convoluted journey to find that if R is half an odd integer, we can't find a monic polynomial with integer coefficients for which R plus SI is a root. So anyway, what's the point? The point is we need R in Z, so Z adjoined I is the ring of integers of Q adjoined I. Okay, and I know I got a little convoluted there. Are there any questions about, yeah?
You got your contradiction was squares mod 4 or 0 R naught and S naught. So R naught squared mod 4. S naught squared mod 4. So mod 4, the sum of squares must be 2.
Right.
That's not divided.
Yeah, I guess we're looking at this. We need this to be an integer. And so in order for this to be an integer, I need 4 to divide the numerator. And by looking at the numerator mod 4 and using the fact that R naught and S naught are both odd, we find out the numerator is 2 mod 4. And 4 doesn't divide, 2 is not 0 mod 4. And so some deep mathematics here. So we can't have R be half an odd integer, and going all the way back to. Thanks, I appreciate it, Ben. Yeah. Great question. Okay, so yeah, this is the ring of integers. We computed our first ring of integers, and we, unfortunately, we're not the first people to compute this. This was, Gauss did a lot of work with these integers, and so these are called the Gaussian integers. And I think at this point too, I'll make a little aside about new things that happen in these analogs of the integers. And one that's particularly confusing, at least I noticed for me and my students, is we have stuff other than plus or minus 1 that divides 1. We have new units. So a unit is a divisor of 1. Okay. Now, in the normal integers, plus and minus 1 are the only units. So units of z are plus minus 1. And we'll talk more about units. The third lecture is going to be about a lovely theorem called Dirichlet's unit theorem, or Dirichlet if you prefer the German pronunciation. So we'll talk more about units, but I just want to kind of point out, did we get any new units in this new ring of integers? And yes, we did. So in z adjoint I, we have the new units. New units plus and minus I. And each unit comes with its inverse, right? You kind of get a second unit for free unless it's its own inverse. And so I times minus I is negative plus 1. So this is a new unit and its inverse. And it turns out these are going to be, yeah. Mm-hmm.
Found any polynomial for which we could get where we could find a lot of our everything becomes a solution. We did that by multiplying x minus r plus si and minus r minus si. But is that usually the only way to find a polynomial? Find such.
Yeah, so that's a great question. This, I guess kind of this is the technique I always think about, and we'll maybe today we'll define something called we'll mention something called the characteristic polynomial. But this is kind of the this is the way. So it if when you do this, you're either going to get the smallest possible monic polynomial that your element of your number field satisfies, or you'll get some power of the smallest possible monic polynomial that your element satisfies. Like here, if s was 0, we just get x minus r squared. So we can kind of like, we can see, oh yeah, this polynomial is too big, but the minimal polynomial of r is x minus r. Or, if r is a proper rational number, we clear the denominator and then we get the integer polynomial that's not monic. So that's a great question, and that's going to be essentially off the top of my head. This is how I cook up. If you ask me to cook up a polynomial, a monic polynomial that your element in your number field satisfies, this is what I'm going to do. And what we'll end up doing is just change to each of the different roots as we go through. Yeah, we'll talk more about that for sure. Great question. Okay, cool. So here's Z adjoined I. Here's our new units. We got our ring of integers. Very cool. So I want to quickly go into the other example. So our other example is k equal q adjoin the square root of minus 3. Okay, so we do the same thing as before. I will spare you all the details, and we find out that z adjoin the square root of minus 3 is in the ring of integers, just like before. Okay, yeah. So in this case, you get x minus r plus s square root of minus 3. Our q basis for k is 1 in the square root of minus 3. There's a lot of q bases for k, but that's one I'll pick right off the bat. And then we have x minus r minus s square root of minus 3. Okay, cool. So same thing as before. The polynomial that square root of minus 3 satisfies is x squared plus 3, and the two roots of that are square root of minus 3 and negative square root of minus 3. Okay, cool. And so as before, we get x squared minus 2r plus r squared minus a negative plus 3 s squared. Okay. So we do, yes. Oh, yes. Awesome. Thank you so much. Got too excited about the 3. So now we do the same thing as before to figure out that, yeah, if r and s are both integers, then this polynomial is a nice integer polynomial, monic integer polynomial. So we get z adjoin the square root of 3 as our ring of integers. And then if r is a half integer here, what we end up getting is, well, 2r is twice a half integer, so it's an integer. And what we end up getting is r naught squared over 4. And as before, we can figure out that the denominator of s has to be 2 in this case. And so we'll get plus 3s naught squared, all of that over 4. And as we know, r naught and s naught are odd numbers. So their squares mod 4 are 1. So we got 1 plus 3. And we need that to be divisible by 4. Bingo. So it works out. We actually do get elements that look like r naught plus square root of minus 3 s naught over 2. So r and s can have denominators, can have 2 in their denominator. And it turns out that the ring of integers of this number field is going to be the set that looks like, how do I want to denote this? A plus b square root of minus 3 over 2, where a and b are normal integers. So we get more stuff because of this square root of minus 3 and the fact that it lets us have a numerator divisible by 4. And the way it turns out, you can actually just write this as z adjoined 1 plus the square root of minus 3 over 2. Okay. So questions about this? I know we skipped through the computation a little bit more here, but it's the same as before, just we get a 3 now, and that saves the day. We can have these denominators. So it's a little subtle. You know, when I first saw this, I was just like, oh, just be square root of minus 3, throw that into z, and we're good to go. But you get some yeah. Yes, yeah. So A and B, good call. Yeah, if I had so up here, if R naught was odd, and then S naught was, well, wait, right, I can't have 1/2 plus square root of minus 3. That won't have a nice monic integer polynomial as a minimal polynomial, because then I just have that's a great point. Right, then this would just be 1/4. This would be some integer, and that polynomial would not be in the integers, it would be in the rationals. To make it in the integers, I need to clear that denominator, and then it wouldn't be monic anymore. So yeah, A and B with same period. Excellent point, thanks for that. Yeah, my apologies there. I'm used to just writing it like this right here. So I guess maybe a better way of writing it would be A plus B times 1 plus square root of minus 3 over 2. A and B and C. All right, cool. Wow, classic. I think I got 5 minutes left here. So questions about these two computations? All right, so it turns out that we've kind of seen it all. You know, I'm studying number fields. I get number fields by throwing in a root of a monic irreducible polynomial. I'm, going to be cautious here. Start with the quadratic polynomials. I mean, we could start with the linear polynomials, but those don't actually give you an extension of Q. They just give you Q. Throw in a half to Q and you get Q. So with the quadratic polynomials, we have two cases, basically. From the quadratic formula, you notice you only need to join the square root of D. That's the only thing that really extends your number field. And we have two cases. One, the ring of integers looks like this if D is congruent to 1 mod 4. And otherwise, it just looks like this if D is not congruent to 1 mod 4. And we can see exactly why that congruence mod 4 comes in, because we have to have that numerator be divisible by 4 in order to have R be a half integer. Okay, so let me just kind of briefly scroll through and figure out what I want to skip and what I don't want to skip. Okay, cool. So yeah, we have lots of fun stuff here. Here's the norm and trace, and that gets to that wonderful question about these polynomials that elements satisfy. So that's definitely worth checking out. If you Google norm or characteristic polynomial, norm of an algebraic integer, Wikipedia is the best mathematician of our time and will tell you all those things. But I do want to talk about a little bit in the last few minutes about what happens with factoring, because one of the best things about the integers is unique factorization into primes. We have this wonderful theorem, the fundamental theorem of arithmetic, which is a fancy old way of saying number theory. The fundamental theorem of number theory is that every integer factors uniquely up to plus or minus 1, so we can see those units popping up a little bit, but up to plus or minus 1 into a product of prime numbers. And that is so useful for us when we're trying to understand things about the integers, because we can just focus on the prime numbers. We can just focus on these multiplicative building blocks. So beautiful theorem. What happens here? Do we still get that beautiful theorem? And or I guess what happens to our integer primes? So if I take 5 in z adjoined I, 5, if I expand that out, I get 4 plus 1. So 5 no longer prime. In fact, it splits into 2 primes. These two things are now my primes. So that can happen. We lost 5, but we recovered these 2 nice, wonderful primes here. Let's see, 2 in and I should note, actually, these are called the Eisenstein integers, after Eisenstein. Really tragic story, Eisenstein. I believe he died before the age of 30, but made a lot of contributions to mathematics in his few years, which makes me feel like I haven't done too much. So let's see if I can remember how 2 splits here. Do I get 1 plus square root of minus 3? No, that won't work. Goodness gracious. Can anybody help me out here? Okay, cool, awesome, good stuff, good stuff. I had a great professor in undergrad, and he would always pretend to be confused and get the class to answer, and I've adopted the technique unintentionally. So I get 1 plus 3 over 2, which happens to be 2. So 2 splits into these. Did I mess it up? Oh, dang it. Yeah. In the back of my head, I knew that was going to mess up, because this is actually a root of unity right here. Oh, what is it? Let's see. Maybe does 2 remain prime? Anyway, let's move on. Okay. Just real quickly, I know I'm over time, and I don't want to steal Christelle's time. So what can also happen? We'll figure out how 2 factors later. Okay. Okay. This is an open question. We'll so we'll figure that out later. So what can also happen, and I think I actually checked these ones using a computer algebra package, because that is much more reliable than my brain. So you can have primes stay prime. So 3 is a prime in the integers, and if I look at 3 in the Gaussian integers, it stays prime. So and I wanted to talk about norm and trace, because we can actually prove some of this by using some tools with norms. And then another thing that's kind of the weirder thing, you can imagine a number factoring into some numbers, or a number being prime and staying prime. The weird phenomenon, and the one that's always the rub when you're trying to prove stuff, the primes that seem to always give you trouble when you're trying to do computations, are the ramified primes. And so, for example, 2, if I do 1 plus I and I square it, that's 1 plus I squared, I get 1 plus 2I minus 1, and I multiply that 2I by minus I. So minus I is a nice unit, right? So 2 is a unit times some other number squared. Right, exactly. Exactly. I'll that's a great point. I'll put that in there. Stays time in okay. Awesome. Yeah, being inert. You know, you think about like doesn't do anything. It doesn't change. So they're the ones that split, but instead of splitting into 2 primes or 3 primes or 18 primes, they have powers of new primes in them. So 2 is no longer prime. Here's a factorization of 2. And it looks like it's the square of another prime. And it turns out 1 plus I is prime in the Gaussian integers. It's a prime element of the Gaussian integers. And so, you know, it's they're primes that become squares or cubes or whatever in these new extensions. And that's kind of weird. You know, you think of like a prime as like this kind of solitary thing, and maybe it breaks apart into distinct new primes, but there's going to be a few that just are a power of another prime. And so another example of this is 3 in z adjoin the square root of minus 3, or 1 plus the square root of minus 3 over 2. 3 now factors as minus square root of minus 3 squared. So this is like the new prime 3, and 3 is a square now. So that's ramification. And okay, I'm coming up on my 5-minute mark. And the last thing I want to say is I highly encourage y'all to maybe, if you're new to algebraic number theory, it would be great to read about norm and trace a little bit, start kind of talking about how to show things are prime or not prime by looking at their norms, and then really disappoint yourselves. Because it turns out that this lovely property of unique factorization that we love so much about the integers doesn't quite work. In the integers, 6 is 2 times 3. That's the only way to write 6 as a product of 2 prime numbers. Or I guess negative 2 times negative 3, but okay. To units, that's the only way to write 6. Here, these are really 2 distinct ways of writing 6. And these elements don't break apart more into prime elements. They can't be broken apart anymore. And the punchline here is this issue led Dedekind and Kummer to introduce the notion of ideals. So if you've seen a little abstract algebra and heard about these ideals, that's where they come in as a response to this disappointment in not having unique factorization anymore. And amazingly, they're kind of able to fix it. Okay, so I'm gonna go ahead and stop right there before I steal any more of Christel's time, and thank y'all for your attention. I guess I should ask for